Hello, welcome to Petrochronics, a research group and extension project focused on petrochronology and its geodynamic implications.
We in Brazil that also has an international network of collaborators. They presently reside in Brazil, Australia, Finland, Germany, Italy, Switzerland, and the US.
Petrochronology involves several areas of the geological knowledge. We seek to disseminate it in a judicious yet clear and accessible manner.
In our researches, we use macro and microscopic observations, combining fieldwork, detailed petrography, thermodynamic modeling, processes dating, geochemical characterization, and much more.
From the natural record, we seek to characterize and quantify petrological processes in representative samples, generating comprehensive datasets that are interpreted considering the geodynamic processes that govern the Earth system.
We want to share research, from the basic concepts to the state of the art, promoting courses, spreading work results, and providing collaborations between institutions and people.
We understand that open science is vital to take down barriers to knowledge, and we prioritize the collaborative and open nature of our research. We also propose discussions on integrity and responsibility in the scientific environment.
As values, we believe in diversity, representativeness, and access to information. We seek to mirror these values in our initiatives.
On the YouTube channel, we promote the PTT Talk series, which are presentations on methodologies and advances in cutting-edge research with petrochronology.
Our actions also include the organization of lectures, courses, workshops, and meetings open to the community.
On Instagram and Twitter, we share, on Tuesdays, photos of outcrops and rocks in the field, illustrating geodynamic processes.
And, on Thursdays, photos of thin sections with microscopic features with interesting minerals and textures, reflecting different reactions and petrological processes.
So, if you work with petrochronology or are interested in related topics, be sure to follow us and get in touch. We want our community to grow even more. See you!
Hello, everybody. Welcome to our PTT talk with Dr. Coralie Vesin. We are here today, four of us hosting the talk. I'm Mayra Tedeschi. I work at the Geological Survey of Finland. I'm here with Catarina da Paz. She's a master's student at the University of São Paulo, Brazil. And with Sonia Ouati from University of Brasilia. Thank you, Coralie. It will be a pleasure. It's a pleasure to have you here today with us in our PTT talk.
Thank you. So good morning or good afternoon to everyone. Giving a brief introduction about the Petrochronics Research Group, we are a team of researchers working with petrology, geochronology, and geodynamics to understand how the Earth's crust has changed over time. Our research combines fieldwork with techniques such as isotopic dating and thermobarometry, focused on the tectonic history of rocks and mountain belts. One of our main activities is the PTT Talk, that is a space to share ideas and research with Brazilian and international scientists. Specifically talking about this session, the PTT Talk is one of the Petrochronics sessions where we present methodologies and research results in petrochronology. We always invite a special guest from this field to share their knowledge with us, and today we are pleased to invite Coralie to give this special talk. I would like also to invite everyone to watch and to check out the previous editions of the PTT Talk, which are always recorded and available in YouTube to watch whenever you want. And now I'll hand it over to Sonia, who will introduce Coralie to us.
Hello, everyone. Good morning or good afternoon. I don't know when you are going to see that. I'd like to give a brief presentation about Coralie's background. So Coralie is currently a postdoc researcher at the University of Bern in Switzerland. She earned her PhD from the same institute after completing her master in Earth and Planetary Sciences at the University of Lorraine in France. Coralie's research focuses on oceanic serpentinisation, particularly looking at the successive stages of this reaction. And to study this, she has developed a geochemical toolbox that uses the in situ trace element compositions of serpentine, along with the oxygen and boron isotope signatures, to decipher the conditions of serpentinization, including the temperature, pH, and fluid compositions. And for a deeper time perspective, she also investigates the hydrothermal alteration of archean comatites. So thanks again, Coralie, to share with us your work today. And I pass the word again to Maya to give us some introduction about what she's going to present for us today.
Yes, thank you, Sonia. So Coralie will present the talk Unravelling the States of Oceanic Serpentinization insights from trace elements and oxygen and boron isotope compositions of serpentine. I will read a brief summary of her talk. The main transfer of aqueous fluids from hydrosphere to the lithosphere occurs during the hydration of the oceanic lithosphere, including the serpentinization of mantle peridotites. The hydrothermal alteration of those ultramafic rocks, meaning silica-poor and magnesium-rich rocks, play an important role in Earth's water cycle and occur at various tectonic settings, including mid-ocean ridges and passive continental margins. The interaction between seawater and ultramafic rocks occur at different temperatures, pH, and fluid composition in successive states of serpentinization. Those states are best recognized by textural domains in which serpentine crystallizes, including mesh texture after olivine and bastite texture after orthopyroxene. The use of in situ analytical techniques is a robust approach to reconstruct the varying conditions of serpentinization. For instance, while the oxygen isotope composition of serpentine is directly temperature dependent, the boron isotope composition can reveal pH variation during serpentinization. Additionally, the trace element composition of serpentine is a powerful tool to investigate the serpentinizing fluid composition and its probable evolution during the water-rock interaction. So thank you again, Coralie, and I wish you a good talk.
Thank you. Thank you very much for this very nice introduction and for this invitation. I'm really, really happy to be here. So as Katarina, Sonia, and Mayra explained, I'm going to present today the main outcomes of my PhD thesis, where I focused on the oceanic serpentinization and especially the different stages of oceanic serpentinization. And I'm going to show you how complex this can be and how those in situ measurements can be really helpful to distinguish all the stages using different geochemical tools. And I would like to acknowledge my thesis supervisors, Daniela Rubato and Thomas Petke, but also my co-workers, such as Michel Ulrich and people I've been working with, especially at the SINS facility with Anne-Sophie, Etienne, and also Marguerite to be a collaborator in this work. So I like to start this talk by recalling that actually the concept of seafloor spreading is quite new. It's from the second half of the 20th century, and after the first mapping of the ocean floor has been done by Mary Thorpe and Bruce Heason in the 60s and 70s. And so this very detailed map could reveal different structures on the ocean floor, like, for instance, those high relief in dark blue, but also some deep deep structures along some coasts here. And so this theory of seafloor spreading have been theorized by Hess, and so this is still quite new, and I think it's important to remember this. And for the sake of this talk, I will focus on the mid-ocean ridge systems, so which are these high relief here in dark blue, which are the most dynamic and continuous tectonic features on Earth. So let's go to the to how the ocean forms briefly. So when the ocean forms, it starts after divergent forces that causes the crust to become thinner, which creates a localized thermal uplift, and this enhances the rifting stage of the continent. We have a system of normal faulting that leads to the gradual subsidence of the crust, and the asthenosphere, so the mantle asthenosphere, rise close to the subsurface, and this stage represents the juvenile stage of the opening of an ocean due to passive tectonic divergent forces. And then in a more mature domain, we have the spreading ridges that are active where the magma erupts at the seafloor, creating a newly formed oceanic crust. There are two types of spreading ridges, the slow one and the fast one, which they differ in the spreading rate. And the fast ones are characterized by strong magma supply, a symmetric extension, and a uniform layering. Layering of the crustal structure, whereas the magma budget on the slow ones is poorer, and this results in an asymmetric spreading and a more complex structure. But in any case, in all of those cases, in the passive margin and in the mid-ocean ridge, these are all very important because this is where the Earth interior meets the hydrosphere. And so what I mean by that is that the seawater can circulate through the oceanic lithosphere in all of those cases. And this leads to major processes for chemical fluxes between the Earth interior and the hydrosphere, which mainly occur in the hydrothermal systems that are present on the ocean floor. Just as a definition, we can define a hydrothermal system as consisting of a heat source with two connected reservoirs and a fluid circulation which enable heat and mass fluxes. And so this is very important because this will change the composition of the oceanic lithosphere, not only the oceanic crust, but also the mantle below. And here I want to emphasize this newly formed lithology that are the serpentinites, that derives from the hydration of the mantle peridotites. And how does it look like in real? So on the left here, you can see a photo of a typical serpentinized hardugite from a drill core from the mid-Atlantic ridge. And this forms after the hydration of the ultramafic rocks from the mantle, so the peridotites. The peridotites are mainly formed of olivine, orthopyroxene, plus or minus clinopyroxene, and this is represented on this very simplified sketch here on the right. And after the circulation of fluid, there are some new minerals that form, such as serpentine, and there can be also other minerals with brucite, magnetite, chloride, talc. But here what we want to focus on is the serpentine because this is the main product of this reaction. And so how does it look like? We have the olivine domain and the orthopyroxene domain. And when we have the infiltration of the fluid will first infiltrate at the grain junction of the olivine, and the serpentine will form in what we call the mesh rim texture. Then with more and more fluid input, we will have more mesh rim, and also the olivine cores get smaller because more olivine reacts to serpentine, and at some point the olivine course, can also get serpentinized in what we call the mesh center. So the serpentine will crystallize in this mesh center. And then at some point, the serpentine will also replace the orthopyroxene, and the pseudomorphic replacement of orthopyroxene is called bastite. And here I really want to emphasize that those three textures are very important. These are the three main textures in which serpentine crystallizes. And I will come back to those three textures a lot during this talk. And so why do we consider serpentine so much? Well, it's because this is the mineral that also contains the most water, up to 13 weight % of water in its in the crystallographic structure. And so serpentinites are very important on Earth because they compose up to 20% of the seafloor. They are found worldwide and in several tectonic settings, including the mid-ocean ridge and the passive margin that I showed you before, that I introduced before. And so this is why the serpentinites are considered to be the major recorder of hydrothermal circulation on the ocean floor through time, not only nowadays, but also in the past. And as I showed you, the serpentinization is not a single event, but rather successive water uptake into the rock. But I also want to emphasize that even if we know for a long time now the serpentinization is this successive water uptake, this is not always easy to show it or to understand what's going on during the reaction, because this is a very simplified sketch that I show you here, but how it looks like in real, this is more or less what we have to deal with. It's a very complex structure. We have lots of veining through the rock. We have those olivine-rich domain that we can see on the right. So it's the cross-polarized micrograph of a microscope with those very poppy colors. Then we have the orthopyroxene on the bottom. We have the vein, the serpentine vein, and so all the serpentine are these green minerals a bit everywhere. And so it's very complex, and so this is why we need so much this those in situ analysis. So to introduce a bit of field localities on this map here, all the spots and all the colored spots are where serpentinites have been found. It doesn't mean that we don't have it somewhere else, it's just that we have samples from here. And for the purpose of this talk, I will present results from serpentinite that have been recovered from the passive margin of Iberia and Newfoundland, and also from mid-ocean ridge, from the mid-Atlantic ridge and the Hess Dip. I also have investigated samples from ophiolites, so from past oceanic lithosphere that are now emplaced on land. And I will show some results from the Ligurian ophiolites and the Samai ophiolites. And as we can see on this sketch here, having access to those ophiolites can be really interesting to understand the hydrothermal circulation in the past lithosphere. And we still, in some cases, in some ophiolite, we can really see the same structures that we see on the ocean. So in this talk, there will be 4 main parts, and they will all answer, or they will all be related to a specific geochemical toolbox that will help to answer a certain question. And so, as I showed you, or as I explained in the introduction, the conditions of serpentinization of the successive hydration events can be revealed by the microscale chemical investigation of the serpentine. And so we start from the hand rock sample, and then we take a thin section, we do all the petrography as usual, and then the first part of the result that I'm going to show you today is how we can use the major elements and the transition metals, so trace elements, how we can use those signatures to trace any potential chemical exchange during the reaction. On the second part, I will use the fluid mobile elements composition to track the fluid circulation through the rock and try to reconstruct the source and the composition of the serpentinizing fluid. We can also use strontium isotopes, but for the sake of this presentation, I leave it aside. Then on the third part, I will show you how we can reconstruct the temperature of the reaction using oxygen isotope composition of serpentine, and also how we can correlate it with fluid mobile element and what it can tell us. And then in the last part, I will explain how we can also reconstruct the pH of the reaction, or can we also investigate the sources of the fluid. And for this, we use the boron isotopes, and we can also correlate it with oxygen isotopes and fluid mobile elements. So let's dive into the first part. So in the chemical exchange during the serpentinization, I showed you before the first stage of serpentinization is the mesh rim texture, so serpentine crystallizing in mesh rim. And on those two plots, we have the silica plus alumina on the x-axis, and here on the y-axis is the magnesium iron. And on the second plot on the right, we have the magnesium number and the aluminium content. We have the serpentine, let's say the structural formula of the serpentine plotting here, and going towards that direction, we have the brucite composition. Going towards that direction is the tar composition. And here we can see that all the serpentine crystallizing in the mesh rim, they tend to be between the serpentine and going to the brucite. So it's quite known that during the serpentinization of olivine, we tend to have a bit of brucite co-crystallizing with the serpentine. So this is quite normal. And then we have the mesh center serpentine. And here we can see there is also around serpentine a bit less brucite. But what is quite interesting is that we are a bit enriched in alumina compared to the mesh rim. There is more alumina in the mesh center than in the mesh rim. And this is quite unusual because there's no alumina in the olivine. The alumina must come from somewhere else. And so if we check the composition of the bastites, so I recall the bastite is the serpentine crystallizing after orthopyroxene. Then here we can see that there's a lot of alumina, and also it's around the serpentine, the normal serpentine composition. And so here we can see that we have chemical heterogeneity of the major elements, and especially alumina, on the small scale between the serpentine textures. And already from here, we could argue that during the crystallization of serpentine in the mesh center, so on the second stage, there is probably also a simultaneous serpentinization of the orthopyroxene, where there's a bit of alumina coming from the orthopyroxene being redistributed in the mesh center. And so this is quite interesting to see that. And if we use, and it is quite interesting to see that, sorry, and if we check also on those nice chemical maps, so everything that is in color here is serpentine. To be more precise, it's lizardite. Lizardite being the low temperature polymorph of the serpentine. So everything that is in color is serpentine, and it represents the magnesium number of serpentine in different textures. We have mesh rim and mesh center in the first one, mesh rim center and bastite on the second one, and here it's a bastite. And what we can also really nicely see on those on those chemical maps is this chemical heterogeneity on the small scale between the serpentine textures, so for instance between the mesh rim and the mesh center, but also within a single texture. Here in the bastite, we see all those different zonation in magnesium number. And this shows the importance for microscale analysis. And this is why we can have a very good spatial resolution using in situ measurements. So this is what I show with those spots here. I can show you how precise we can be and how well we can target the different serpentine textures. And so this will be the main part of this whole talk, is that we can really track the different serpentine textures, and then we can combine the different signatures of different methods. So this was for the major elements. And now I want to introduce a new concept using the transition metals. So transition metals, it's for instance, nickel, chromium, vanadium, scandium. And if I take this first sketch that I showed you with the olivine domain and the orthopyroxene domain, we know that from the mantle composition, the olivine is enriched in nickel, and the orthopyroxene is more enriched in chromium, vanadium, and scandium. And so this difference in composition leads to a different nickel-chromium ratio between orthopyroxene and olivine, and a different vanadium content. This is what I show you in this example on the right, where we have the mantle olivine plotted on the lower right part, and the mantle orthopyroxene on the upper left part. And those transition metals are supposed to be fluid immobile, which means that they should stay in their initial texture, right? And so when we serpentinize this peridotite, we expect the mesh rim and mesh center to be enriched in nickel, and the bastite, so the serpentine in bastite, to be enriched in vanadium, scandium, chromium. And what we could say is that if the serpentine in bastite indeed plots around the mantle orthopyroxene and the serpentine mesh around the mantle olivine, then there is no element redistribution, and we have this sequential serpentinization. However, if we see some kind of element redistribution between those two end members, then we could argue for a simultaneous olivine orthopyroxene serpentinization. And so we can use those chemical heterogeneity of the transition metals to assess their temporality between the serpentinization of olivine and orthopyroxene. So how does it look like in real? These are some of the results that I want to show you, and just will not go into detail, but what is quite striking is that in most of the cases, there is no transition metal redistribution. There is limited chemical exchange. Maybe we have a bit of vanadium uptake in those mesh rim here, but it's not so striking everywhere. But here in those two samples from the passive margin, we see a very nice trend between the orthopyroxene and the olivine mantle. And here it is argued for simultaneous serpentinization that is recorded by transition metals. And so if we combine those results with what I show you in the beginning with the alumina content that tends to be higher in the olivine center, in the mesh center, then we could say that there, in some instances, in some cases, we have a simultaneous serpentinization of olivine and orthopyroxene. And even if this was suggested in the past, using these kind of plots and analysis, we can actually show it in the chemical traces. So this is pretty cool. So now we go to the second part, where I want to investigate the fluid circulation and the fluid composition of the fluid composition. So we're going to use the fluid mobile element composition of serpentine, and especially the chlorine and the boron, because these are two of the most important fluid mobile elements in seawater and in serpentine as well. The seawater has a certain amount of chlorine and boron, and the chlorine and the boron, they don't have the same behavior when it comes to fluid or mineral. The chlorine is what we call has incompatible behavior, meaning that the chlorine will preferentially stay in the fluid. On the other hand, the boron has a compatible behavior, meaning that it will preferentially get incorporated in the solid phase, and in our case, in the serpentine. Which means that in a system where we have the same partitioning of the chlorine between the residual fluid and the serpentine, the resulting chlorine-boron ratio in the serpentine should stay constant, because we have the same amount staying in the fluid, the same amount staying in the boron, and so this chlorine-boron ratio is constant. However, if we go into a more closed system, meaning that we have a fluid that interacts more with the rock, we are more in a rock buffered system, then it means that the fluid will get passively enriched in chlorine. And in this case, the serpentine crystallizing from this more saline residual fluid, the serpentine will have more chlorine than the chlorine crystallizing from the seawater. Which means what we see in the serpentine is that the chlorine-boron ratio will increase. And so by using this chlorine and boron concentration in serpentine, it can help us to assess whether the fluid composition has evolved from a seawater to a more saline residual fluid. So this is the concept we came up with. And if we checked in nature what we have, so these are some examples from the passive margin serpentine. What we can see is that in some samples we have a constant chlorine-boron ratio, which means that we are in a fluid-dominated system with constant input of fresh seawater. And this is what we have in most of the cases. But also in the same sample, we can also see an increase of the chlorine-boron ratio. So we have the chlorine on the x-axis and the boron on the y-axis. And in some cases, we can have an increase of this ratio, and it's usually in those bastites, texture, which means that when it comes to the serpentinization of orthopyroxene, we tend to have a more evolved fluid composition. So what we can see here is that we usually have, or in most of the cases, we have an evolution of the fluid composition from seawater to saline fluid. We could do the same for the mid-ocean ridge sample, but what I want to emphasize here is that on the same plot, the chlorine versus boron, all of the points, in gray are the passive margin samples. So it's basically those results plotted here again. And in the mid-ocean ridge serpentine, we see that the chlorine-boron ratio is much higher than the one in the passive margin. It's usually above 25, whereas in the passive margin is usually below 25. And this was one of the main results of our study, because it shows that there is a different incorporation of chlorine and boron in the two different tectonic settings, which is quite important. And this shows that the chlorine-boron ratio could be a great tool for discriminating a tectonic setting where serpentinization occurs. So this was quite impressive, and we can have some hypotheses why this is the case, but honestly, it's still pretty new or yeah, we need to do more research on that for sure. So this was the case for chlorine and boron, and I also want to show you that we can use another fluid mobile element, that is the strontium, in serpentine to try to check another composition of the fluid. So what we have here on those two plots is that we have the strontium versus boron, and on the plot on the right is just the other way around. We have the boron versus the strontium. And I plotted the mid-ocean rich serpentine in the light gray, here and here, and the passive margin serpentine on with the dark gray here and here. And also, I have plotted what's the composition of a normal mantle, of the seawater, and of different kinds of reservoirs that we can find on the ocean floor. So we have the altered oceanic crust, we have hydrothermal fluids in a sediment-hosted environment, we have the marine sediments pore fluids, and these are the same here. And so now we can see first that the passive margin, that the serpentine in the passive margin tend to be more enriched in strontium than the mid-ocean ridge. And this could be due to an exposure to sediment equilibrated fluid, or at least where we have a lot of sediment. And knowing this, so because we have those this strong discrimination, I want to show you that we can use those discrimination plots to try to reconstruct the tectonic setting of past oceanic lithosphere. So here I'm going to show you some results on serpentinites that I've collected from ophiolites. In the first case, it's from the Ligurian ophiolites. We know from tectonic studies and magmatic studies on those samples that what we call the internal ligurites, so it's a specific part of the Ligurian ophiolite, we know that they formed from a mid-ocean ridge, in a mid-ocean ridge setting. And we see here that they plot mainly, not always, but mainly in the mid-ocean ridge area. On the other hand, we have the external ligurites that is thought to represent an oceanic continental transition, so in other terms, a passive margin. And here we see that those samples are much enriched in strontium than their internal counterparts. And so what we can see here is that we are consistent and coherent between the new results when we investigate the hydrothermal alteration of those rocks. These match the tectonic setting that has been previously studied, which shows that we could actually use or we could actually investigate the hydrothermal history of those rocks to try to reconstruct or to help reconstructing the tectonic setting, which is quite impressive in my opinion. And on the other side, on the right side, I want to show you the example of the other ophiolite that I have investigated, which is the semi-ophiolites. And we can see that most of the samples plot in the mid-ocean ridge affinities for the strontium and the boron composition. Yes, thank you very much. We come to the second part of this presentation, where now we're gonna jump to the oxygen isotope or more isotopic parts, and starting with the oxygen isotope of the serpentine. So the oxygen isotope systematic, so we usually express this in delta O18, which is where we look at the ratio of two isotopes.
One second, it's just that we can understand from your presentation because it's very well illustrated, but we cannot see your pointer in case
okay.
But it's totally fine, just in case you want to use. Okay.
Sorry. Thank you. That is good. Thank you. So for the oxygen isotope, there are three isotopes: the 16, 18, and the 17. But for this ratio, we only use the 18 and the 16. And so how it works is that we measure the ratio of oxygen 18 and oxygen 16 of the sample. We compare it. We compare this ratio to a standard. And then basically what this means is that we look at how much the ratio of the oxygen 18 and oxygen 16 deviates from the standard value. And so this delta oxygen 18, we measure it in our sample, so in our serpentine, and we can kind of not predict, but we can expect how this value will be, because the serpentine that crystallizes from a fluid, the fractionation between those two reservoirs, so the oxygen isotope fractionation between the fluid and the serpentine, this is temperature dependent. This is what we call a fractionation factor, and the fractionation factor is temperature dependent. Throughout the years and the decades, there have been a lot of fractionation factors that have been proposed. And here I just show you the latest one. But we see when we have the temperature versus the fractionation factor, we see this yellow line. And we see that at lower temperature, so temperature lower than 300 degrees, we have a large fractionation, which means that if we know the composition of the fluid, of the oxygen isotope composition of the fluid, and we measure the oxygen isotope composition of the serpentine, then we can calculate the temperature at which the serpentine crystallized. But this is not so simple because there are some analytical challenges. So very briefly, the serpentine group is composed of three main polymorphs, which are antigerite, crisotyl, and lysodite. They have different crystallographic structure, which means that they have different fractionation factor that changes with the mineral, and they have a different instrumental mass fractionation, which is specific for this machine that we use here on the left. This is a secondary ion mass spectrometer, commonly named SIMS. And this is very dependent on the mineral that we are analyzing. This is why we need a matrix matching reference materials. And this has been developed quite recently, or 2018. And this was the reason why this whole study was possible. And as you can see here on this image, I think it's quite nice to see how tiny everything we work with is. So this is called a aluminium ring with indium inside, where we have the standards that are mounted in epoxy, and we have our samples that are actually cut out of thin section, and they are pressed into an indium that are then put in the aluminium ring. So we can see how tiny everything is. This is 2 millimeters per 2 millimeters. And in those standards, we have the olivine, because the olivine standard is used for to assess the stability of the machine, of the instrument, and to see how our analyses are repeatable. And then we have the serpentine standards that are used for the reproducibility and further calculation. And then we have our sample measurements, then we measure again the standards, etc., until the end of the session. At the end of the session, what we have is that we have the we can see the stability of the instrument, where we have the average for all the different standards. And when we know the reference value of those standards, of those reference material, we can calculate the average over during our session, and then we can calculate the mass fractionation. And as we can see, the mass fractionation is not the same for the different mineral. This is why we need really a matrix matching standard. But this is not only for the oxygen isotope. This is quite normal in every kind of measurement, but I thought it was quite important to say it here. So now for a bit of results. Here I show you most of the results that I've obtained during my PhD thesis. On the left we have the passive margin, on the right we have the mid-ocean ridge. And this is not the same scale. On the y-axis, that represents the delta O18 of the serpentine, but the green bands in the two plots, they represent the mantle composition. And on the left, we see the temperature, or we can see that if we have high delta O18 in the serpentine, this means a low temperature of serpentinization, and vice versa. What we can observe from those two plots is that in the passive margin, the delta O18 mainly range from 4 per mil up to 14 per mil, whereas in the mid-ocean ridge, it goes down to 1 per mil up to 6, 7 per mil, which would mean that in the mid-ocean ridge, the serpentinization tends to occur at a slightly higher temperature compared to serpentinization in a passive margin. And also, another interesting fact is that when we look at the difference between the delta O18 of serpentine in the mesh rim versus in the bastite, for instance, on the right plot, if you look at the second sample that is called S003, we can see very nicely that we have an increase of the delta O18 between the mesh rim, that are the open circle, and the bastite, that are those triangle. And even though it's not the case for all of the samples, this tends to be a general trend in most of the sample. Also on the left, the sample S012, this is also what we observe. And so it would mean that it seems that there is a decrease of the temperature during the serpentinization from the crystallization in the mesh rim to the crystallization in the bastite, which could reflect the progressive exhumation of the mantle to the seafloor. So we can imagine that we have the mantle being exhumed on the seafloor, and while it's being exhumed, we have the circulation of the seawater, and so we can, the serpentinization seems to record these different difference in temperature. So this is also quite nice, because same as I said before, even if these are concepts that were thought to be true before, here, thanks to these in situ measurements, we can actually show this with those geochemical tools. However, The oxygen isotope systematics are not only temperature dependent. The first equation is the same that I showed a few slides before, but the delta 18 of the serpentine is not only dependent on temperature, but it can also depend on the fluid composition, on the initial rock composition, and on the water-rock ratio. What we can see on the right sketch is that if we consider a fluid being seawater, it means that the composition is 0 per mil. This is the composition of the seawater. But if we tend to have a fluid that has a higher delta O18, it means that the serpentine that will crystallize from this fluid will have a higher delta O18 as well. And these different fluid composition are usually impacted by the circulation of this fluid throughout the rock, and this could be related to this water-rock ratio when we consider a fluid-dominated and a rock-dominated environment. So here, it is important to remember that the oxygen isotope composition can be impacted not only by temperature, but also fluid composition, which reflects the interaction between the fluid and the rock. So now if we want to calculate the temperature of the serpentinisation based on those oxygen isotope, we need to be sure that, or we need to find a way to see that the initial fluid composition was the seawater, or if not, it could have impacted our serpentine composition. This is why we came up with another concept where we want to match and to correlate the delta O18 composition of the serpentine with the chlorine-boron ratio that I presented before. Because as you remember, the chlorine-boron ratio can show us if we have a typical seawater composition or a more evolved composition. How it will look like is that if we have an increase of delta O18 in our serpentine, but with a constant chlorine-boron ratio, this means that the fluid composition hasn't changed and that the variation that we see in the delta O18 reflects a temperature change. On the other end, if we observe an increase or a variation of chlorine-boron ratio in the serpentine, but with no variability in the delta O18, it means that it seems that there is a change in the fluid salinity, so a change in the fluid composition, but with no impact on the olivine isotope composition. We can also have the case in between, where we observe a positive correlation between those two proxy, where it could mean that we have a temperature variation and a change of fluid composition. And on the other hand, we can also have this negative correlation, which means that we have a decrease of temperature, but then we have more input of fresh seawater, and so it's less saline. And so this is the theory of what we can observe in our in situ measurements. But now I want to show you what we actually observe in our sample. Here, this is an example on the middle plot. This is an example of a sample from the passive margin, where we have the chlorine-boron ratio in the x-axis versus delta O18 of the serpentine. We have it for the mesh rim, for the mesh center, and for the bastites. And on the right, we have a similar plot that I showed you before with this fractionation factor. We have the temperature on the x-axis and the delta O18 on the y-axis. And what we have is that we have different curves for different fluid composition. And the first The first red line actually represents the seawater composition that is at 0. But if the fluid gets hydrothermally altered, which means that it interacts with the rock around and then the oxygen isotope change, then we will have higher delta O18 of the fluid. And the second line is at 2.4 per mil, which is thought to represent the highest delta O18 ever recorded in a hydrothermal vent fluid. So if we look step by step, we start with the mesh rim. The mesh rim, we can see on the middle plot that there's a bit of variability in the chlorine-boron ratio and also in the delta O18. And so here we could argue that we have a fluid composition that tends to change a bit and is not only seawater composition. Then we have the serpentinisation of the mesh rim. But here what we can see is that we have a rather constant chlorine-boron ratio. So here we could argue that we have the same, or at least we have no evolution of the fluid composition during the crystallization of the mesh center. Then we have the bastite composition that tends to be have similar delta O18 composition of the mesh center. And then the bastite has actually 3 zonation. It's a very complex bastite, and it seems that we have an increase of the chlorine-boron ratio and then a decrease. And so if we check here, we see a decrease of temperature, a general decrease of temperature from the mesh rim to the bastite, and we could argue for some variability in the fluid composition, and so the temperature that we measure or that we calculate could be a bit underestimated due to this variability in the fluid composition. So this is an exercise that I show you just for one sample, but we could do this for all of the samples, of course. Here the main message is that we have an evolution of the composition during the serpentinization, and in the passive margin we tend to have a lower temperature of serpentinization than in the mid-ocean region. Now, to the last part of this presentation, I want to focus on the boron isotope systematics. And so, similarly to what I've showed you before for the oxygen, for the boron isotope systematics, the boron isotope fractionation is also temperature dependent. This is what we see on this plot in the middle. On the x-axis, we have the temperature, and on the y-axis, we have the fractionation, the isotope fractionation. And we see that it depends of the temperature. But it has also been argued for years that it's also quite known or quite expected that the boron isotope also fractionates differently depending on the pH. So here on this plot, this is the pH on the x-axis, and we can see that the different species of boron that are present in the seawater, in the fluids, they also differ, or their fractionation differ according to the pH. However, it has been shown, or it has been shown very recently that actually at temperature higher than 50 degrees, the pH might have a negligible effect on the boron isotope fractionation. So this is to keep in mind, but I will come back to this later. And so similarly to the oxygen isotope systematics, the boron isotope composition of serpentine will also depend on the boron isotope composition of the fluids. We can see in this nice paper review, or in this plot review, that all the different fluid reservoirs have different delta 11 boron composition. We have the seawater that is at plus 40 per mil, but then the hydrothermal fluid can be negative up to 10 per mil, etc. And also on this plot here, when we plot the boron content versus delta 11 boron, we can see that there's different fluid reservoirs that have different composition. So this might have an impact on our boron isotope composition. I will come back to that later. For a bit of result now, what I've seen in my samples is that we have measured delta 11 boron that are quite homogeneous within the serpentine textures. So if we check for each sample and each texture, this is quite homogeneous in the sense that this is quite, this is all within uncertainty for most of them. But we have also cases where we see that we see also a difference or a variability between the textures. So this is what we see with those red arrows and the yellow arrow. And in other case, we have quite similar or quite homogeneous boron isotope composition within the textures. So we can see what it means. Can it be only a temperature effect? Can we see this difference, this variability between the mesh rim and the bastite? Is it only due to a temperature effect, or is there another parameter that comes into account? And so to do so, we can try to compare or to correlate the boron isotopes with the oxygen isotopes that we measured for the same sample. So here I take, here I will construct with you this plot where we have the temperature on the x-axis. This is exactly the same that I showed you before, it's just that the x-axis is swapped. So we have the low temperature on the right-hand side. And here, this is the delta 018, so the oxygen isotope composition for the fluid at 0 per mil. On the other axis, we can plot the boron isotope fractionation curve. That is also temperature dependent. And what we know from the oxygen isotope is that for a certain sample, I give you the example where we have the delta 018 of the serpentine that ranges between 2.7 and 6.5 per mil. And this represents a decrease of temperature from, let's say, 230 degrees down to 140 degrees. So it's a certain amount of variation of temperature. And so because we know that from the oxygen isotopes, we can say what is the expected boron isotope fractionation according to those temperature variation. And so this is what we see. We would expect a variation of 9 per mil in this sample. So we have this 9 per mil that is predicted from the temperature variation that has been calculated from the delta 018. But in this case, in this sample here, we have a variability of 22 per mil. between the mesh rim and the bastite, which means that this variability cannot be only explained by a decrease of temperature. However, in this sample, in this sample here, this actually represents around 9 per million. So here we probably have a good correlation between the oxygen isotope and the boron isotope systematics. And in this sample here, we could have competing parameters with maybe a decrease of temperature, but also a change of the fluid composition. And so to test this hypothesis, I want to show you here on this plot that I showed you a few slides before, the boron content versus delta 11 boron, where we have all those different reservoirs with the seawater, the hydrothermal fluids, where there's no sediment, this hydrothermal fluid where there's sediment, the altered oceanic crust, etc. When I plot my samples here, so these are the samples from my study, from my thesis, these plots here, quite close to the seawater, but also going down to this hydrothermal fluid reservoir here. If we check sample by sample, so this sample with the large variability in delta 11 boron, they actually they are the one here in yellow, and we can see that this one actually could correspond to this hydrothermal fluid reservoir, so meaning that this is most likely that we have an evolution of the fluid from seawater composition and down to hydrothermally altered fluids. For the other sample, these are quite close together and more in this seawater or hydrothermal fluid, but that has less evolved than the other one. And in this sample, this is also the case. So in most of the time, we could see a potential evolution of the fluids, but in some cases that are stronger than in other cases. So this was the example for the mid-ocean ridge sample, but I also want to show you quickly for the passive margin. And those one, we clearly see that they're much less, there are less variability. It's all close together. It's very low delta 11 boron and very close to the hydrothermal fluids in the sediment hosted environment, which would make sense if we remember the tectonic setting that we have in the passive margin. So in this ocean continent transition, we are closer to the to the continent, and we can have, or it's easier to have input of sediments than in this deep mid-ocean ridge setting. On top, I plot other data from the literature. What we can observe is that in the oceanic serpentinites, we tend to record delta 11 boron between 5 per mil and 40 per mil. And for another perspective, in the 4-arc setting, we have much lower delta 11 boron composition down to -13 and also up to +35. So this shows the large variability in those different serpentinites and in the different setting, which shows the importance to be able to reconstruct the whole history and the whole conditions using different systematics and different signatures, especially when we can compare the different isotopic systems with fluid mobile elements, for instance. So this brings me to the end of this presentation, where I hope I could show the importance and how powerful this geochemical toolbox is, and how we can better assess the conditions of serpentinization, not only for the successive stages, so not only for those three main stages, but also between tectonic settings. What we could have, what I showed you during this whole presentation is that we have chemical heterogeneity in all those different signatures, and this shows that having access to in situ measurement, this is a real strength in order to really track every stages. And also we have observed this chemical heterogeneity in the different tectonic settings, for instance, with the chlorine-boron ratio, but also the strontium content, and in the boron isotope composition. And I briefly showed you that, but because so we could apply this geochemical toolbox not only on present-day serpentinites, but also on the past oceanic lithosphere. And we observed geochemical similarities between the past and the present. And this shows that we could use the hydrothermal history of past oceanic lithosphere to better understand, well, the hydrothermal processes, of course, but also maybe to distinguish the tectonic setting based on the hydrothermal processes. So this kind of an open question, and of course, there's more work to do on this, because here I focused on the passive margin versus mid-ocean ridge, but we have also 4-arc setting and other kind of setting that could be investigated. So I thank you for your attention, and I'm looking forward for receiving questions.
Thank you so much, Coralie. It was really interesting talk, and you gave the background, and you did a really impressive amount of work with the different tools. Congratulations. It was really interesting.
Thank you.
It was really great. We invite everybody attending the talk. If you want to send comments, questions, we will start the discussions, but please use the chat to send your comments and questions. Coralie, I have some questions, but I will start then from the beginning. I was very interested because you present the textures, and they are very interesting, and also this issue that the aluminum should come from another mineral. And I was wondering, because at least I'm not familiar with the ultramafic systems, but then for other systems, usually aluminum is quite immobile. Then I was curious about this. Could it be the case that actually you had like some pyroxene core relict or something that then around it had this growth maybe of olivine and the serpentinization? Or what would be your main evidence that there was this migration? Or actually, do you have any other evidence in addition to the composition that you could explain that?
Yeah, I see what you mean. Unfortunately, I don't have all of those chemical maps, but when we check the chemical maps, we can see when we have those orthopyroxene and the serpentine crystallizing in the orthopyroxene or around, we see that those are enriched in aluminium. But we can also have the an enriched mesh rim that are further away. It's always around the orthopyroxene, so it's not a huge element mobility, of course, because the aluminum is immobile, or it's supposed to be immobile, but we see that there's still some mobility, and it's always a few hundreds of microns of mobility, but still this is quite...
There is something.
There is something. And I gave the hypothesis of the oxygen, of the orthopyroxene being the source for the alumina, but it could be also spinels, because we have lots of spinels in those rocks, or we have some spinels, and so we could have also a release of alumina during the alteration of spinel that then goes into magnetite, and then some alumina could be lost also. So it's always quite limited, but we still observe that, which is quite
Amazing. So you have like some gradient. That's really interesting.
Yeah, unfortunately, I don't have on this presentation, but
No problem. Thank you.
Thank you.
I would like just to make a small comment that I have pronounced Sonia's surname wrong before. So it's O-A-D. Is that right, Sonia?
It's actually Oadai.
Oadai. Yeah, I'm sorry, Sonia, but thank you for.
That's okay. I know it's not so common to have these letters.
Thank you.
So I would also like to congratulate you, Coralie. It was an incredible presentation. It's very detailed work, so you have a lot of work. And I'm not used with the subject, but I would like to ask you if you want to work with another elements, transition elements, and try to look at the correlation with the serpentines.
Yes, so here I showed the example of the nickel-chromium ratio and the vanadium, but actually we have tested for other transition metals, also the scandium, the zinc, the manganese. But then the zinc and the manganese are a bit particular because we could see more mobility. But for the scandium and cobalt, we all see the same. For the same sample where we see this variability or this redistribution in the vanadium, we observe the same in scandium and other. So it's quite impressive.
Yeah, so this one were the best, like to try to make this correlation.
Yes, exactly.
Very nice. Congrats.
Yes. Thank you.
Coralie, congrats again for your complex and great, really fascinating work. I really like it. I have a question actually about the carbonation. You showed in the beginning your petrography, texture, etc. And I was wondering if you have carbonate in the matrix or maybe in the impregnating the bastite, actually the orthopyroxene. And relating to that, because you showed the strontium that is higher in this bastite and the oxygen isotope too. So I was wondering if there is some relation with this mineral existing in the matrix or not.
So yeah, thanks for your question. In those particular samples, we don't have lots of carbonates. And when we had that, we really tried to stay away from them. Okay. And we really checked that we were not in contact with carbonates because these could have an influence. But because we have those very precise, high resolution in situ measurement, we could really target the serpentine and not the carbonates. And I guess that if we would have had even tiny carbonate inclusion in the serpentine or something that we wouldn't have seen, the strontium content would have been much higher anyway.
Okay.
Because here it's I say it's high because it's high for serpentine, but it's still just a few tenths of ppm. So.
Okay, so it cannot influence the oxygen isotope, for example, to control the temperature.
No, because that would be another stage, like a much later stage. I don't think that we would have serpentinization and carbonation at the same time, or at least that's not what we observe in our sample. So even if we have carbonation, it happens much later, and so this will not influence the serpentinization stage.
Okay.
And also because the oxygen is a major element in those systems, we would need to have a huge amount of carbonates to really make a difference, and we don't observe that in our samples.
Okay. Yeah, thank you.
Thank you.
So we have some comments on the chat. So yeah, we have some like, hi Coralie, thanks for your presentation. It was a great presentation. Great topic. And we have a question from Lucas Tesser. Did you map your samples using EPMA before perform the in situ seams analysis? Do you believe that the standard EPMA mapping techniques could promote loss of volatiles, chlorine and fluor, for instance?
That's a good point. Thank you. Thank you for this question. Yes, so we mapped the samples using EPMA before doing any other kind of measurement. So usually we did microprobe, then we did the scenes analysis, and then we did the laser ablation ICP-MS for the trace elements. And I don't think that the EPMA mapping technique could have an influence on the loss of volatile, because serpentine are quite soft mineral. They're quite fragile, and we really made sure that we have a short dwell time and sweep time, so that the microprobe spot doesn't stay too long at the same place, because otherwise we would have strange artifacts. So because of the method that we use, I don't think we would have a loss of volatiles. And yeah, I hope that answers the question.
Thank you, Coralie. I have another question for you. It's related also for the chlorine. I found it very interesting, the scheme you had, like, to discuss the evolution of the fluid. And I was wondering, in addition to that, let's say, I don't remember exactly the words you used, but let's say more evolved fluid, do you think other factors could play a role, like the input of different waters for the setting? Sometimes, because in Brazil we had a similar situation to the Red Sea, and then we wonder, could it be something like that affecting the chemical results?
Yes, that's also a good point. The thing is that the serpentinite that we collect now in those passive margin and in those mid-ocean ridge, we don't have the timing where they formed. In the sense, we don't know if they formed just at the beginning of the opening or later, or we have some hypotheses, but we don't know. And so it could be, I don't know, it's a hypothesis, but it could be that the serpentinization in the passive margin happened when there was still much more saline seawater fluids, and it doesn't have the same seawater composition than the big ocean that we have now. So it could be this, or it could be a seawater that has interacted with other lithologies, with the ocean crust, oceanic crust, sediments, or But this could be also an incorporation feature. It could be the partitioning of chlorine that might change depending on the setting, because we have a different, a different temperature or different things like this. And we don't have, there's not so many studies, like experimental studies that are, that really investigated the parameters influencing the chlorine partitioning.
Yeah, there are so many parameters that can affect that it's difficult to constrain like a specific one. But I found it very interesting, this, and I'm very impressed with the combination. Thank you, Coralie.
Thank you.
So we have another question from Marco. Hi everyone, great presentation, Coralie. What is the implications of applying this whole methodology to Archean serpentinized rocks? Do you intend to do it?
Yes, that's a very interesting. Thank you for this question. So actually, for my postdoc project, I was working on arcane serpentinized rocks. And the initial idea was to do some kind of similar or apply the similar methodology, but then we focused on other projects based. There's so many things to do on those archean rocks that we decided to go another direction, but we could do the same. The problem is that in archean serpentinized rocks is that there's not only the hydrothermal history, but there's so much more metamorphic history that could have influenced tectonic reworking, and it would be very difficult, I guess, to apply the same methodology because also we don't have the low temperature polymorph, but we have the high temperature polymorph. So is there any? We don't know if there's some partitioning that also occurs during this transition from the lizardite to the antigorite, etc. So I guess at some point this could be done, but I didn't have time to yet. But that could be a very cool outlook.
Thank you, Coralie. Sonia has another question, right?
Actually, it's like, it's a question because you just talking about the tectonic settings, but I will jump this one. It was about the, you studied the mid-Atlantic ridge, but I was thinking, what's about the difference between slow and fast spreading, ridges? So if you investigated that, if you have any insight about it. And
yes, that was also a big question when I started my PhD project. And bottom line is that we didn't see any difference, whether it's a slow spreading ridge or a fast spreading ridge. We don't see any difference in the oxygen isotope, boron isotope, nor trace elements, etc. So I don't know. I guess that the temperature was similar, or the fluid was similar, but I was also wondering if the spreading rate had an influence, but we didn't see any. But
yeah, and you have also any insight about the other types of serpentine, because you in your presentation you showed the lizardite mainly in a bastite and mesh, but what about the antigorite in other settings? I don't know if you there is a way to have a spot in like antigorite in mantle wedge or something like that, and their structures.
So in the mid-ocean ridge samples that I have investigated, we found in one sample antigorite. So it was mainly serpentine. It was mainly lizardite because it's the low temperature polymorph. In one sample, we have an antigorite vein. And because it was not the focus of our study, we didn't really went deep to that. And so I didn't investigate any mantle wedge or four arc setting. But I guess this would have an influence. And they have actually a few studies that have been done previously by other researchers, where they also checked the transition from the lizardite to antigorite in those mantle wedge. So with increasing temperature with increasing temperature, we see this transition of those two polymorphs, and then they investigated the trace element composition and any potential trace element loss and everything. So in my studies, I didn't investigated antigorite in those oceanic setting, but I know that there are some studies that have done this. And I guess it would change, it would have an impact on the oxygen isotopes, for instance, but in the trace element, I don't really expect it, I would say.
Okay. Thank you again, Coralie.
Thank you.
Thank you so much, Coralie, again for joining us this afternoon with this very impressive and amazing talk.
Thank you.
I would like to invite everybody. This month is special, so we have two talks. At the end of the month, we have Dr. Jan Frankovski from the Geological Survey of Romania talking about high precision age in sedimentary sequences. So I would like to invite everybody to join us as well. So thank you very much to everybody who joined the talk, and Coralie again, and our special invited host Sonia and Katarina. Thank you.
Thank you very much for organizing.
Thank you, guys. Ciao.
Thank you. Bye.